Hey, welcome back. We're going to now have a series of three fairly short lectures on using solar energy, using the sun directly as an energy source. Going to start off by we're going to talk about the sun as an energy source, and then we're going to talk about solar electrical energy systems, and then solar thermal energy systems. So getting electricity directly from the sun and getting heat directly from the sun. And first, we're going to talk about using the sun as an energy source. What are the unique characteristics? What are the unique things we have to consider using the sun as an energy source? So first off, let's talk about what causes seasons, because how we place our design elements for solar systems, solar panels, solar electric, solar thermal, water distillation, passive solar design. It's all related to where the sun is in the sky at different times of the year. So what causes the sun to be in different places in the sky at different times of the year? Think about this for a second, and you got any ideas? Well, it's because the sun is tilted, the Earth is tilted on its axis at about 23 degrees. And as it goes around the sun in during the year, it presents during the summertime, the northern hemisphere. In the northern hemisphere is more directly pointed toward the sun. It gets the sun's rays more directly, and that the southern hemisphere gets the sun's rays at a steeper angle, and so there's less solar energy per square foot, and so it's cooler. It's warmer at the equator and warmer on the north. It's warmer in the northern hemisphere. And you might think, well, what causes seasons is in the summer, the sun is actually, the Earth is actually closer to the sun, and in the wintertime it's further away, therefore it's hotter in the summer and cooler in the winter. But that's not true. In the northern hemisphere in the summer, actually, the sun is further away, and it's closer in the winter. And so let's take a little bit more look at that. So here's what happens. So we have the sun tilted on its axis, and if this is the equator, that's at about 45 degrees, maybe roughly where we are on the Earth, a little further north. We're about at 40 degrees from the equator, and so Earth tilted at an angle of 23 degrees. Sun's rays coming in parallel to the Earth. And so in summer, you can see the sun is coming directly onto this location. Spring and fall, it's a little further up. In winter, it's actually tilted away from the sun, and so it gets less energy per square foot. So what causes variations in day length? So that's the season, but why are days different length? And you can look here, and this shows you for any given month of the year, and for different places on the Earth. This is at the equator, 30 degrees north, 50 degrees north. We're at 40, so we'd be halfway in between here. 60 degrees north, that's like up in Alaska. 50 degrees north is in kind of middle northern Canada. 70 degrees north is way, way up there, like in. So here's showing again. Variations in day length are caused by the tilt of the Earth on its axis. And interesting. So what happens is, you look here, the Earth is spinning around its axis where this line is in the north. And I think I have a slide that shows this a little bit better later, so I'll explain that later. But it's related. So you can see here that at the equator, the day length is the same all the time. And when we get further north from the equator, then the day length goes to 24 hours a day for a few months of the year. So it's light all the time. Because if you look here at the North Pole, you see how it's spinning in the summertime, spinning around here. So somebody standing here, as they spun around the North Pole, they'd be in sunlight all the time. Now, the opposite is true in the winter. If you look here, and somebody is located right here, right next to the North Pole, way far northern latitudes, then you see here in January and part of December, it's actually dark all the time. There's no hours of daylight. And another interesting thing is that in spring and fall, the day length is 12 hours a day everywhere on the planet. That's because the Earth again is rotating around this axis of the north-south poles of the Earth. And you see here that one rotation, half of the rotation brings you into darkness. And at the equator, half of the rotation brings you into darkness. Anywhere on Earth, the days are 12 hours long. Here's a 3D view of where the sun is in the sky at different times of the year for a building. So in the wintertime, you notice here's east-west. And you might think, well, the sun rises in the east and sets in the west, but it only rises directly east and sets directly west on 2 days a year. That's the spring and the fall equinoxes. And the rest of the year, when we're going towards summer from the equinox from March 31st going towards summer, then the sun every day is rising just a little further north, just a little further to the north of east, until it's quite far north of east and actually shines on the north side of a building in the morning and afternoon in the summertime. And then in the winter, in the fall equinox, September 21st, the opposite happens. So the sun rises on that day directly in the east and then slowly works its way till it rises quite far to the south of east and then just takes a very short arc through the sky and sets quite far to the south of west. And so to give you an idea, here in Iowa, the height of the sun above the horizon at noontime is about 70 degrees. So it's about 70 degrees off the horizon. And in the wintertime, it's only about 20 degrees off the horizon. So that's the distance it makes. And here it is. This is where I used to live. I lived on a road that went directly east-west, and so I could observe that as I was driving into the dome every morning. And this is the sun's rising here right directly on the road, right directly on, very close to the equinox. It looks like it's just a little to the south of it, so maybe it's just a little before the equinox or just a little after, going towards winter. And then you can see I've drawn in here, this is maybe where the sun rises in the middle of the winter, quite far to the south of east. And then again, it works its way across here, throughout the season until it gets to springtime. And then it works its way, in springtime, it works its way north until on June 21st, on the summer solstice, it goes as far north as it's going to go. And then it works its way back so that by the fall, it is directly east again, if that makes sense. Different at the equator. At the equator, the sun's almost always directly overhead. So that causes quite a bit of change in thinking about where you'd place solar panels or wind turbines solar panels or building elements. So here's an example of how you might think about how the sun would hit a building at different times of the year. This would be in the winter time where the sun's quite low, and this would be during the solstice, the equinox on March and 21st and September 21st, and then this would be the sun at its maximum angle. And the interesting thing about this is you can take advantage of this to design a building so that it shades itself in the summer and lets sunlight deep into the building in the winter without any kind of mechanical devices. You just put the overhang over the windows at a certain distance so that in the summertime the window's completely shaded, but in the wintertime the sun is going to go deep into the building. Then this shows where the sun rises at December 21st, March 21st, and June 21st. So the sun rises, you can see quite far to the south of east, sets quite far to the south of west, and then in the summertime it rises quite far to the north of east, as you can see here, and then during the equinoxes it rises almost directly to the east. And another interesting point is you might think you always have to face directly south. But if you're within 20 degrees of true south, so from 100 to 80, then the cost in solar gain is minimal. It's almost the same, 100 to 80. But if if you go from 100 if you go from directly facing south to 2 degrees off south, you still get 92% of the solar gain. Even at 45 degrees off, you get 70% of the solar gain. So, we want to face directly south when we can, but we can actually take fairly significant turns off south and still not lose very much energy. This shows the thermal energy that's gained by a window in different orientations. So, for example, this is a horizontal window, which would be a window on a flat roof like a skylight. And then this is an east or west facing window. This is a north facing window, and this is a south facing window. So if you can think about it, what would be the ideal heat gain in a window? Well, you'd have very little heat gain in the summer when you don't want extra heat in the building, and you'd have tons of heat gain in the winter when you do want the extra heat in the building. And so let's take a look at what happens with each of these window orientations. So flat skylights on the top of a flat roof, you notice that it gets the minimal amount of energy in December, February, March, spring, fall, winter, and it gets the maximum amount of solar energy in June when you don't want it, in this June, July, August when you don't want it. So flat skylights are actually pretty bad solar collectors because they collect solar energy when you don't want it and they reject solar energy when you do want it. East-west windows are also pretty bad. They do the same thing. North window, not so bad. I mean, it collects a little extra energy in the summertime, but it doesn't really add anything to it. Doesn't hurt you too bad in the summer, but it doesn't add anything to you in the winter. What's really cool here is the south-facing window, and you see minimal amount of energy. This is, I think, a south-facing window without even any overhang. Minimal amount of energy in the summertime when you don't want it. Maximum amount in the winter. So south-facing windows for solar gain, very good. You're going to put windows in a building anyway, might as well favor the south. You can put too many windows in the south and overheat a building, and we'll talk about that a little bit more when we talk about buildings. But just to let you know what the characteristics are of windows in a building. And then we talked a little bit about how you want to how things change when you're at a different angle to the sun. So let's take a look at that. If you've got the sun coming directly overhead onto your the Earth, then a 1 mile wide beam of sunlight is spread across a 1 mile length of surface of the Earth. But if the sun is coming at an angle, let's say the same 1 mile section of sunlight coming into the Earth at 30 degrees and at an angle in the wintertime, then when it hits the Earth, that 1 mile of sunlight is going to spread across 2 miles. So you'll actually have half as much energy per square foot as when it's straight on. So what this means is that your solar collector wants to face directly at the sun as often as it can. And that this is also one of the reason why it gets colder in the wintertime, because you just have less density of sunlight. And then this is just another way of showing that, where you see that the equatorial regions of the Earth, they get solar energy in a much more direct way, and that the higher latitudes on the Earth, then they get solar energy at an angle, coming in at an angle, and it spreads over. They don't get as much per square foot. So with all that, what's the best angle to place a solar panel? Well, the best angle, if you're not going to move the panel, the best thing to do, if you could, it would be to move the panel to face the sun all day long so that it was perpendicular to the sun at any point. But that's often costly to do. You can do it, but it's often costly to do. So if you're not going to move your solar panel, the best rule of thumb for solar electric is latitude. You want to put the solar panel at the latitude wherever you are. So in Iowa, that's 40 degrees. If you were in Maine, that's maybe 45. If you were further north in Canada, that might be 50 or 60 degrees. If you're further south, like Hawaii, that's about 20 degrees. And so, another thing to think about is if you were, for some reason, wanted to maximize the amount of solar energy you got in the summer, then take the latitude and subtract 15 degrees. So actually take this panel and lower it so it's at a flatter angle to the sun, because the sun is going to be higher in the sky, and you'll get more energy in the summer and less energy in the winter. You might do this if you had a system that was pumping water for a farm and you wanted to maximize the amount of energy you got in the summer. You didn't care in the winter because you really weren't going to be pumping water then. And then for maximum winter gain, you'd go latitude plus 15. You might also do this summer angle for the summer gain if you had a summer camp or something, summer cottage, and you wanted to put solar there and you weren't going to be there in the wintertime. You just want to maximize the gain for the summer. Then you'd put it at latitude minus 15, flatter. Now for maximum winter gain, put it at latitude plus 15. So 40 plus 15 would be, 55. Whoops. Sorry about that. Let's get back to... Whoops. Not sure why that's doing that. Okay. So, then the rule of thumb for solar electric or PV photovoltaic is latitude. Now hot water is different in that with hot water it puts out solar electric panels actually work better in the wintertime when it's cold, so you don't get less energy from a solar panel just because it's wintertime and it's cold. But solar hot water, the efficiency of solar hot water is directly related to how cold it is outside. And so the summertime when it's hot, they're very efficient. If you lose some solar energy, it doesn't matter as much. So with solar hot water, what you typically want, what you want to do is pick it up so that it's latitude plus 15. It favors the winter sun. But if you're in doubt, just go with the latitude. Now let's take a look at how to calculate how much energy you'll get from a solar electric panel. Whoops. Okay, let's try this. So we're going to use a site that's was developed by the National Renewable Energy Lab. It's used by all the major solar contractors, like Ideal Energy uses it. Let's go. Whoops, we have an internet connection here. Hold on just a second. It should come right up. All right. So it's called PV Watts, and it's run by the National Renewable Energy Lab. National Renewable Energy Lab is in Golden, Colorado, and we'll be visiting that facility during the next course. So we go ahead and let's just take a look for Fairfield, Iowa. Go. Just Google PV Watts, PVWATTS, and then it's looking for weather data. So we'll put it's taking a minute for all this to come up. See, there's quite a bit of weather data here, and let's just go with the one from Moline. It's going to be close enough. We could select another weather station. Now what I like to do is I like to put in PV system size of 1 kilowatt, and then I can always scale it up, because a 10 kilowatt system will put out just 10 times the annual energy of a 1 kilowatt system. So I'll just use 1, and then I can scale it up for however many kilowatts I want. So I have to choose what kind of a module. If I use a standard module that has an efficiency of about 12%, premium module maybe 18 to 20%, thin films only about 5% efficient. Let's just stick with a standard module. And then we have to choose what type of rack, and it could be a ground mount rack or a roof mount rack, or racks that actually track the sun. And we'll talk more about those another time, but you can track the sun just sort of in one axis, or you can track the sun, directly facing the sun all the time. So let's not worry about, we'll just go with a fixed rack with a roof mount. And don't worry about the system losses. Now, the tilt is going to be important. It comes as a default of 20 degrees, and we're actually at 40. So let's go ahead and put 40 degrees. And then you can't, sometimes you can't always face south with solar panels. And so in this program, 180 degrees is straight south. If I was going to do 90 degrees off south to the west, it would be 180 plus 90, which is 270, or 180 or 90 degrees off south going east. That would be due east. That would be 180 minus 90. So so in this case it would be 90, or 270 would be the east and west directions. And there may be different reasons why you have to do that. For example, the solar panels that are just being installed in the dome, they face west. And so to get an idea of how much energy they'd put out on an annual basis, you'd put in here 270 degrees and whatever angle they're at. Now your smartphone often has a app that will measure angles for you. If you don't know the angle of your roof or something, you can kind of just run that app, put your smartphone on, and it'll tell you. So let's go ahead and look at what we're going to get out of this solar system. So this is telling us we're going to get about 1,327 kilowatt hours per year. Remember I said Fairfield's about 1,300 kilowatt hours per year. And what's interesting is this tells me what I'm going to get every month of the year for that system. So notice that in January, the minimum is in December when I get 69 kilowatt hours, and the maximum is in May, June, and July when I get about 130. In August, actually, all three of those months I get about the same, and almost twice what I get in December. And so you can get an idea of if I want to design an off-grid system, I'll probably be looking at December so that I can, in the worst month, I'll get enough energy. And if I'm looking at a grid-tied system, I just know that I get 1,328 kilowatt hours for the year, and it doesn't matter so much what month I get it in, because months I get extra, I can the power company will let me credit that towards the months when I don't have as much. So that just gives you there's how to calculate for any place. Really, this will let you do it for any place on Earth. How much solar, how much kilowatt hours you're going to get for each kilowatt of solar. And I think that's the end of our PowerPoint on the sun as an energy source. And again, you can play around with this and see. Let's go back and see what happens. So we got 1,327 if we are faced directly south at 40 degrees. But let's take a look if we go to 20 degrees and we face 270 degrees, which is roughly what the dome system is. It might even be 15. And let's see what happens if we face it west instead of south. So we go from 1,300 to 1,100. So we lose some. We lose 20% or so. But it's not a deal killer. We still get quite a lot. We still get the vast majority, bulk of the energy that we would get, even if we were faced south, even if we faced directly west. And then what'll happen is that amount of energy we get throughout the day, there'll be more in the afternoon because we're facing west. And some utilities would prefer you to do that because their peak demand is in the afternoon when everybody comes home from work. So back to the presentation. And that's the end of this presentation.